Okay, so we will get into what is called wedge constraint today. Again, another important monster, wedge constraint. So wedge, first of all, let us see what is a wedge. What is a wedge? Any block on which another block can move is called a wedge. Any block on which another block can move is called a wedge. For example, you see I can have a triangular block like this on which you can have another block like this. So this is my wedge. It may be fixed or it may be movable. Both are possible. Or you can have a wedge of this shape. Many shapes are available. You can have a wedge. This is a wedge. Or I can have, you know, something like this, where I can have one block here and there is a pulley and another block. So this is a wedge. Or I can have something like this. So this is a wedge. In its simplest case, I can just have a block and another block, and I could call this wedge, nothing wrong. So generally a wedge can be fixed or wedge can be movable. When we are talking about wedge constraint, we assume wedge is also movable. Okay, when we are talking about wedge constraint, wedge is movable. Wedge is movable. So let us try to uh, understand and see how it works. What is wedge constraint and how it works? The statement of wedge constraint goes like this. Statement of wedge constraint. If wedge and the block are in contact and the contact surface is a flat one, not a curved one, and the contact surface is a flat one, not a curved one, then perpendicular to contact surface, perpendicular to contact surface, acceleration of wedge and block must be same. So let me help you understand this. If you go to this case, here the contact surface between wedge and block is flat. You see, it is not curved. Okay, I previously did not draw it properly also. Let me try to draw it properly. Straight one, yeah. So the contact surface between the wedge and the block is a flat one. In this case, I can apply wedge constraint. What happens if it is curved? If the contact surface between wedge and block is curved, then this condition may fail. This condition that wedge and block, if they are in contact, perpendicular to contact surface accelerations must be same, that condition will fail. We will see that slightly later, but right now, if we assume the contact surface between wedge and block is flat, then perpendicular to contact surface, which means in this direction, in that direction, acceleration of the block and the wedge both must be same. To help you understand it in a much better way, I cannot apply wedge constraint here because this is a curved surface, so I will not apply it. But you look at this case, the contact surface is flat one, so perpendicular to contact surface in this direction, acceleration of block and wedge should be same if the contact is to remain. Okay, similarly here, this is the contact surface, and perpendicular to contact surface, acceleration of wedge and block must be same if they are to remain in contact. Why like that? What is the reason? It will become more clear if you look at this example. See, this is the contact surface, perpendicular to contact surface means in this direction. The block and wedge should have more same acceleration. If they have different accelerations, then they will lose contact. How? For example, suppose the block has an acceleration of 4 meter per second square in that direction, and the wedge has just 2 meter per second square. Then what's going to happen is, in a small time, maybe 1 second or whatever, the block will gain a greater velocity and wedge will have a lesser velocity, so they get separated. Then there is no contact. So if you look here, if the wedge and block are to be in contact, then they should have same acceleration perpendicular to contact surface, provided the contact surface is a flat one. Now you might challenge and say, sir, what if the wedge has 4 meter per second square acceleration, 4 meter per second square, and block just has 2 meter per second square? Then what's going to happen? The wedge is going to gain in small time, whatever it is, even 0.001 second. It's going to gain a greater velocity, and immediately it's going to push the block above it, so that eventually this will also come to some common acceleration, right? It will come to either 4 or whatever. So the wedge and the block will have same acceleration perpendicular to contact surface. That is the wedge constraint. Otherwise, the contact will be lost. So this is a very simple example to understand, but we are looking at more complex examples. For example, here in this case, the wedge could have any acceleration. It could be moving horizontally, but I am looking at its component in this direction. Similarly, the block could be moving in a very complex way, but I am looking at its acceleration in that direction. Okay, so in that direction, acceleration of the wedge and block must be same. If I name this direction as xx dash, so take the acceleration of wedge and take its component along xx dash. Similarly, take the acceleration of block and take its component along xx dash. Both must be having same magnitude and direction, the components. So acceleration of wedge along xx dash and acceleration of block along xx dash must be same. Similarly here, only then they will be in contact. If there is no constraint that they should be in contact, then they can have any acceleration. But if they are in contact, this should hold. Similarly, if the block A and wedge, if they are to remain in contact, then along xx dash, here in this diagram, along xx dash, acceleration of wedge and the block must be same. Similarly, if B and the wedge are to remain in contact, then acceleration of the block and the wedge along yy dash must be same. Okay, why this doesn't work for a curved surface? The problem is, when the block is going in a curved surface, suppose the wedge is not moving, it is at rest. Let's keep it at rest. then already when it is going in a curved surface, there is a radial acceleration v square by r, and wedge does not have any acceleration, but still they are in contact. The problem with curved surfaces is that there will be a v square by r, which doesn't exist in a flat surface. There will be a radial acceleration in a curved surface, which is not there in a flat surface. Flat surface doesn't have radial acceleration because by definition flat surface means the radius of curvature tends to infinity and radial acceleration is zero. So now this failed, the constraint. Why it failed? The block is in contact with wedge. Wedge has no acceleration, but block has acceleration v square by r perpendicular to contact surface, and still they are in contact. So it fails for flat surfaces. So the way you have to apply wedge constraint, sorry, it fails for curved surfaces. So the way you have to apply wedge constraint for curved surfaces is you must subtract this v square by r and then apply it. Suppose if the acceleration of the block in this direction is some a1 and wedge in that direction is a2, then a1 minus v square by r should be a2. That is the constraint. We have to make some adjustment. That's the reason I am not going into curved surfaces, and we very rarely get such a problem involving curved surface. Okay, so far so good. Now, what about the next example here? So, suppose if I call these blocks A, B, and C, then this is my contact surface. So, if wedge and block are to remain in contact, then in this direction, acceleration of wedge and block must be same. Similarly, if wedge and block B are to remain in contact, then acceleration of wedge and block B in this direction must be same. Similarly, if C and wedge are to remain in contact, then acceleration of wedge and C in this direction perpendicular to contact surface must be same. If they are not same, they'll separate. Similarly, here in this direction, acceleration of wedge and block must be same if they are in contact. That is the wedge constraint. So constrained motion means the bodies are constrained to move in a certain way. That is what we call as constrained motion. If bodies are connected by string, they can't just move the way they want. They have to move in a certain way. If I tie a dog to a rope and hold it, the dog just cannot run the way it wants. I am holding it. So it's constrained. Okay, it can only move in such a way. Suppose I am holding a rope and dog is here. Dog and I can move only in such a way that, suppose if I am moving like this and dog is moving like that, my component along the string and dog's component along the string must be same, because the string is inextensible, right? Assuming the string is tight. Okay, if the string is loose, the constraint may not hold, but I am assuming that it is tight or taut, and then I am saying that. Similarly, if a block and a wedge are in contact, and if they have to remain in contact, they just cannot move the way they want. They have to move in a certain way. They are constrained to move in a certain way if contact is to be maintained. Now, how do we use this in problems? We will see. I will take a problem where I'll also show the complete solution also along with constraint. Suppose I have a wedge like this, and let's say this angle is theta, and mass of the wedge is capital M. And then I have a rod okay, and there is a wall here so that this rod cannot, and there is another wall here so that the rod is able to only go up and down. It cannot go to left and right. These walls prevent it. So this is one wall, wall 1. This is wall 2. So the rod is in contact with the wedge right now, and this is a smooth surface. Okay. So basically the system is released. System is released. Suppose if acceleration of wedge is capital A and acceleration of rod is small a, you see the wedge can move only in horizontal direction. It cannot move in any other way. And the rod, what I have here, the rod, that can move only in vertical direction because the walls which are there are not allowing it to move horizontally. Okay. Now, what will be the relation between A and A? How are A and A related if rod always remains in contact with wedge? That is basically I'm asking the constraint. First thing. Second, solve for A comma A, okay, both these quantities in terms of small m, capital M, theta, g. That means you have to completely solve the system by drawing free body diagram, applying Newton's laws and all that. Complete problem. So generally, whenever a problem is given, it may be just a part of the problem. That is like using constraint to relate the velocities or accelerations. That's an easier version. The more complete problem will be where you draw the free body diagrams, write Newton's laws, and also use constraint and solve it. That's the more complete, like I did in the end yesterday, right? I gave two blocks with strings and pulley, and I gave a force, and I said solve the system, get the complete accelerations of both blocks. So I drew the free body diagram, I applied Newton's laws, I used a string constraint, and then I solved all the equations to get the acceleration of both the blocks yesterday to the end. Now I have a similar problem here. There is a wedge, there is a rod. The wedge can only move horizontally, the rod can move only vertically because the walls are not allowing it to move horizontally. The wedge acceleration is capital A to the right, the rod acceleration is small a down, and I am first trying to relate A and capital A, small a and capital A. And later I am solving also for small a and capital A in terms of small m, capital M and theta. Now how do we do this? First thing that you should understand, the wedge and the rod are always to remain in contact. So you cannot just have any arbitrary whatever value you wish, you cannot have for small a and capital A. For example, look at this. Suppose I say capital A is, just as an example, 10,000 meter per second square. That means this fellow is just shooting off like this very fast. Whereas the rod's acceleration vertically is just 1 meter per second square. So what's going to happen here? The wedge is having a huge acceleration and it starts gaining huge velocity and runs away. And after it ran away very quickly here, suddenly the rod sees that, oh my god, I have no support below me and it will fall and hit the ground. It's like, imagine you are standing here instead of the rod. The wedge just quickly went away and suddenly you see that you are hanging in here and you start falling down and land on the ground, and that may be dangerous. So you just cannot give any value of acceleration for small a and capital A. They are related in certain way. If the contact is to remain, they just cannot have any values that you want. The values are related in certain way, and that is what we want to find. Now I will develop this constraint in two methods. One is by using this statement. Okay, we can use this statement and develop the constraint. There is another geometrical way also, which I will do. So method 1 of developing constraint, look at this. Method 1, I'll just redraw the diagram here. So this is my wedge and this is my rod. Okay, something like this. These are the walls. Now you look, this has acceleration a down and this has acceleration a to the right. Now before I go further, it should look very natural that wedge should move to the right only. Why wedge will move to the right? Why something should move? There must be some force in the direction. If you draw the free body diagram of the wedge, okay, there is mg, there is normal contact force by the ground, and there is a normal contact force by the rod. Now you see the point here. This normal contact force by the rod has got a horizontal as well as vertical component. Okay, vertical component could possibly be balanced by this N1 and so on. But my question is, who is balancing this horizontal component of the normal force? So rod exerts normal force on wedge. Rod exerts normal force on wedge. Okay, in which direction? In this direction. That has horizontal component and vertical. Vertical for a minute, forget it. This horizontal, which is acting on the wedge. Who is countering it? Nobody is countering it. That is the reason wedge starts moving to the right with certain acceleration, which I called here capital A. Now, how do we develop the constraint first? So first let's come to the constraint. This free body diagram and all, you forget it for a minute. That was just to tell you that wedge should move to the right because of contact force. Now, what is the constraint statement? This is the contact surface. So we must take a direction which is perpendicular to contact surface, which means in this direction, perpendicular to contact surface. Acceleration of wedge in that direction and rod in that direction must be same. Acceleration of wedge, I am redrawing it here like this, capital A. Okay, instead of drawing it here as a green color, I have drawn it there. And this angle is theta, their corresponding angles. And what about small a? It is like this. I am redrawing it here, small a. Okay, let me just write this down. Now, both these accelerations are there, and I must take their components along that big red colored line. So this component is a sine theta. Why is it a sine theta? This theta is angle with the blue line. Okay, capital A is making theta with blue line, so that component is cos. But I want perpendicular to blue line in this direction. That is a sine theta. If capital A has component sine theta along this, small a, which is perpendicular to capital A, must have cos theta because it is already perpendicular to capital A. So a cos theta. So the constraint is a equal to a tan theta. The accelerations must be related like this for the rod and the wedge to be in contact. Otherwise, they will not be in contact. For example, if I say, you know, capital A is root 3 and theta is 60 degrees, small a should be capital A tan 63. No other value should be there. It should be like this one. So the accelerations of the wedge and the rod must be in certain way and only then contact will be there. And that certain way is, it should be small a is capital A tan theta. So how did I get it? Once again, I took the contact surface between the rod and the wedge and I drew a line perpendicular to contact surface. So that is our direction in which we have to take the accelerations and apply constraint. Now acceleration of wedge is capital A to the right. Its component in this direction is capital A sine theta. That's what I've written here. And small a is vertical, that is the rod's acceleration, and its component along this direction, that is small a cos theta. That is what I wrote here. And from there you get small a is capital A tan theta. That is the constraint relationship. Now I have a different way of developing the constraint also, which I'll show here. So this is my wedge. something like this. Let me draw the ground also. This is the ground. I will show the rod like a line here for convenience. Okay, maybe I'll show it here. I'm showing it as a line for convenience. This rod can move only vertically. Why? Because there are walls which won't allow it to move horizontally. Okay, now look at this. This angle I have taken as theta. Suppose the wedge moves to the right by a distance x. So I am going to move it. So let me see if I can copy this fellow. So I have moved it. Okay, my diagram may not be very complete. Let me I'll just put a dotted line like that. Then okay, this also I'll put a dotted line. So you see the wedge, let us say it has moved by a distance x. The wedge has moved to the right by a distance x. Okay. Now, if the rod is to remain in contact, the rod must come down exactly by this distance. Otherwise, the contact will not be established. This distance. And the horizontal distance was x. This distance was x. Okay. I showed it. I showed this distance x. You know, here also. I'll take a bigger eraser. Okay, I showed the x here also, the wedge mode, and here also, here also. And what about this angle is theta? Can I say this angle is also theta? uh, I'll put it here. That angle is theta because this is also theta. These are, I don't know what you call them, two parallel lines intersected by alternate angles maybe. Okay, now you see the wedge moved by a distance x and the rod had to move by a distance y to maintain the contact. What is the relation between x and y? You can use tan theta is y by x. So y equal to x tan theta. Purely from geometry, I am looking at it. Purely from geometry. Okay. Originally, this was the wedge. And then the wedge moved to the right by a distance x. And the rod can only move vertically. So the rod comes down by a distance y. Wedge moved by distance x and rod came down by distance y. If it doesn't come down by distance y, the contact is not maintained. So it came down by distance y and the contact is maintained. And this angle is theta. You moved this parallel to this, so this is also theta. And that should also be theta because these two are parallel lines and intersected by transversal. So tan theta is y by x, right? So y is x tan theta. Theta is a constant, of course. I'll differentiate this once. If you differentiate y, what do you get? It is the displacement of the rod. When you differentiate, you get velocity of the rod. Okay, should be. And what about differentiation of x? That is velocity of the wedge into tan theta. So even the velocities must be related like this. The wedge cannot have a huge velocity and rod very less velocity. Then contact will be broken. And I further differentiate this. If I further differentiate this, I get acceleration of rod should be acceleration of wedge into tan theta. Acceleration of rod is small a, acceleration of wedge is capital A into tan theta, which is exactly the constraint I got by saying that perpendicular to contact surface, the component of this acceleration and that acceleration should be same, right? So, so that's my wedge constraint, which I can get geometrically also by just visualizing. If this moves by x and that moves by y, then tan theta is y by x. So this way we can develop constraint. So what is the purpose of constraints? How are we using constraints in our course? They are used to relate accelerations of two blocks or wedge and block and so on. String constraint was relating the acceleration of blocks connected to strings. Wedge constraint is relating the acceleration of the wedge and the block which is moving on it. So that is the main purpose of constraints. Constraint just gives you an equation in terms of the accelerations or velocities. But if you want to solve the whole system, you must take the wedge separately, draw its free body diagram, and apply F equal to ma. You must take the block separately, draw its free body diagram, and apply F equal to ma. So I am going to do that now, because constraint is only one part of the problem. If you go back here, if you go back, constraint was only one part of the problem which I asked here. The next part of the problem is solve for A and A. You have to solve for the accelerations of the wedge and the block, and I'll do that now. So how do we do that? First we'll take the wedge. This is my wedge, angle theta. What are the forces on it? There is N1 by the ground, and there is mg, the pull by the earth. So actually earth is pulling it, and also the rod which is there is exerting a contact force N. Okay, so both these forces are trying to push the wedge down, but the ground will not allow, so it is exerting a force N1. Okay, both mg and the contact force by the rod on the wedge are making it go down, and in that process the wedge pushes the floor, and hence the floor pushes the wedge. But anyway, there is no vertical movement, so vertically the acceleration is zero. The only acceleration which you have is the horizontal, which is capital A. Now, who is responsible for this capital A? Actually, this N has got two components. If you draw a line like this angle is theta. So the N has got N cos theta as the vertical component. Before that, how did I get this angle as theta? You see, this line, what is perpendicular to that? This horizontal. This vertical line, the perpendicular to that is horizontal. This N, the perpendicular to that is incline. So if incline and horizontal have theta, their perpendiculars, vertical and perpendicular to incline, should also have theta. Angle between two lines is angle between their perpendiculars. So that way I quickly wrote it as theta. And now I'm splitting N into N cos theta, which is the vertical component. So that N cos theta and this mg together are being countered by N1. And then I have N sin theta, which is my horizontal component. So this is N sin theta. Okay, that middle one is N. So this N sin theta is responsible for the acceleration of the wedge in the horizontal direction. There is no other force horizontally except this. So my Newton's law says that net force, which is to the right, should be mass of that object into acceleration in the same direction to the right. This is my one. So I wrote Newton's laws for this in the horizontal direction. Suppose you say, sir, why are you not writing the Newton's laws in vertical direction? You write it, no problem. You will get N cos theta plus mg is going to be N1. You will get an equation, but it contains a new variable N1, and I don't need that for my solving actually. It's just another equation with a new variable. I don't need that. If you want, you can write that. Now, the rod, if I look at the rod, so let me draw the rod properly. This is my rod, and there is this normal force. What is this normal? The rod pushed the wedge with N. The reaction of that is N pushed the rod with wedge pushed the rod with again N. Okay. Now, if this is the, and there is of course mg of the rod. Okay, earth pulls every object. It's a non-contact force. Now, my question is, this N has a horizontal component, and it should make the rod move to the left. But rod is not moving to the left. Why? Because there are walls which don't allow the rod to move to the left. So actually this N wants to make the rod move to the left. So the wall will counter it, and it will exert some N double dash or N2, let us say. So this is the force by the left wall, not allowing this rod to move to the left. Right wall, will it exert a force on this rod? No, no. Why? Because to start with, the rod has a tendency to move to the left, and left wall reacted. The right wall, even though it may be in contact, it is not, the rod is not pressing the right wall. Okay, and so there is no normal force by the right wall on the rod. Now the acceleration of the rod is A down, so I can forget about the horizontals. Okay, again this angle is theta, so n sine theta is n2. I don't need this equation, I'll call it 4. So the only equation which I need is mg minus n cos theta is ma. That's the vertical direction equation. Why I don't need 4? Because it brings a new variable n4. I don't need that. So what are my equations which are important? This is an important equation. Okay, and this is an important equation. Others involve extra variables. This brings n2 into picture. I don't need that. This brings n1 into picture. I don't need that. Now these two equations, if I write them on the next page, 1 and 3. One is n sine theta is, okay, capital M into capital A. Okay, that is one. And mg minus n cos theta is ma. Mg minus n cos theta is small m into small a. I have to solve for small a and capital A. But the problem is, these are two variables, but there are three variables in the equation actually. How? N is also a variable I don't know. Capital A, small a. Three things I don't know, but I have only two equations. But let's not forget the constraint. So we have the constraint A equal to A tan theta. So I am going to write that here. So small a is capital A tan theta. This comes from constraint. And hence, now I will be able to solve the system. How I will solve the system? Let's see that. First, I have to eliminate n from these equations. So I can write mg minus, what is n from first? Ma by sine theta. I'm putting it in second, into cos theta, is m into small a. Small a is capital A tan theta. So I have now an equation in capital A. So I have mg is ma cot theta plus ma tan theta, which implies my A is going to be mg by m cot theta plus m tan theta. That's going to be my A. So you see, first I developed the constraint between the wedge and the block. I kept it aside. Then I have drawn the free body diagram of the wedge and the block by carefully drawing every force on these systems and showing their accelerations. Then I applied Newton's second law separately to the wedge and to the rod. Then I have solved the system. So I got this. Once you get capital A, what is small a? Small a is capital A tan theta. So I have mg tan theta by m cot theta plus m tan theta. So my problem is completely solved now. This is a problem from the book called Irodov, actually, very tough book, but it brings down all the concepts, constraint, wedges, how to solve, how to draw free body diagram, how to solve using Newton's laws, everything is brought out. Okay, now let's do another question where I will only develop constraint. I am not solving the complete problem. I'll only develop the constraint. What is it? Suppose I have one wedge like this. We draw it. This is the ground. Okay, something like that. There is a rod here. So let me draw another wedge like this. And there is a wall here so that this right wedge cannot move at all. Okay, this is, so this angle is alpha, this angle is beta, and this wedge is moving with an acceleration A. Question is, assuming the rod is in contact with both wedges, assuming rod is in contact with both wedges, find acceleration of rod. This is the question. This is a very complex question actually. We will try to solve it. See, first thing you see, this rod's motion is very strange. it cannot just come down like this. For example, if I try to draw, uh, let me just try to copy this and just try to draw it a bit down. Suppose I copy it and I again paste it and just, oops, suppose I just try to bring this down. See, it was here like this, and I'm just bringing down. If I bring it down, what will happen? It will penetrate this wedge. That cannot happen, right? The rod, so the rod simply cannot come down. The rod simply cannot come down. It cannot create a hole in the wedge and come down. So if the rod has to move, it has to move down also and to the left also appropriately. That means in some direction like that it has to move. That's the problem here. In our previous case, this rod was forced to move only in vertical direction because these walls were there. But now this rod, it has to be in contact with both wedges. It can't just come down because it cannot create a hole in this wedge. That's the problem. So it is coming down also and it is going to the left also. So the motion is very complex. So what I'll do, I'll take an acceleration A1 down and A2 to the left. And I don't know these values. I have to adjust these values in such a way that the rod should be in contact with the right wedge also without making any hole, and should be in contact with left wedge also without losing contact. And in such a way, I have to find A1 and A2. Okay. Of course, this wedge cannot move. This one cannot move because there is a wall which will not allow it to move to the right. If that also moves, and if it also has some acceleration, then the constraint will change. Suppose both the wedges are moving and rod is to be in contact with both of them. Now, then it has to move in a certain way. That is also another problem, the more complex problem. But let's first solve this. So how do I solve? Now, I've got two variables which I have to solve for. So I need two constraints. And I have both the constraints. I have constraint with the right wedge. This is the contact surface. Okay. And perpendicular to contact surface. So I'm drawing the contact surface here. Perpendicular to contact surface means in this direction. Okay. Acceleration of wedge, which is 0. So total acceleration of this wedge is 0. So even its component is 0. So 0 should be equal to acceleration of the rod in that direction. How do you get acceleration of the rod in that direction? You see very carefully. I am redrawing this A2 and A1 below. These are the two components of acceleration of the rod. Okay. If you add these two, the resultant will be the acceleration of the rod. The rod moves down also and to the left also. It cannot just move down because it cannot create hole in the wedge. So it has both leftward and downward components of acceleration. And I have to draw perpendicular to this contact surface, right? This. So I am drawing that perpendicular to contact surface, this direction. Okay. And along that direction, wedge acceleration is 0, of course. So I must take rod's acceleration in this direction. I must take rod's acceleration in this direction. But rod's acceleration has already two parts. So this part also I must take its component in the direction, and this part also I must take its component in the direction. Okay. Acceleration is represented by two vectors here. Both vectors components in that direction I have to take. Now how do I take that? Now let's see what are all the angles. See, angle between A1 and this orange line should be alpha. How do I know that it is alpha? Look, the angle between this incline and horizontal is alpha. What is perpendicular to incline? This red line. What is perpendicular to horizontal? This vertical. So angle between two lines is angle between their perpendiculars. These are two lines with angle alpha. Okay. And the incline's perpendicular is this line, and horizontal's perpendicular is the vertical line, and that angle also should be alpha. Angle between two lines is angle between their perpendiculars. So with that idea, and this is 90, so this has to be 90 minus alpha because total is 180. So what is the component of A1 along that direction? A1 cos alpha. I am writing it towards this direction. And what is the component of A2? Minus A2 sin alpha. Why minus? Because its component is the other way. It's pointing in that direction. So I am writing it minus. So net acceleration along this line is A1 cos alpha minus A2 sin alpha. That is the acceleration of the rod in that direction. But acceleration of wedge in that direction is 0 because total acceleration of wedge is 0. This is one constraint. I've got one constraint now. Okay, that is the constraint with the left wedge. What about constraint with the right wedge? I must also do that. So I'll take this whole diagram maybe. Okay, let me take it to next page. I'll just erase this part right now. I don't need this because I'm applying constraint to the left wedge. Okay, so the contact surface here is this. I'm redrawing it here perpendicular to that contact surface. So maybe I'll draw it here in this direction, perpendicular in that direction. Acceleration of the wedge. Wedge is having horizontal acceleration A, and this angle is beta, right? Angle between the acceleration and this line, that is beta. Okay, and I also have A2 in the same direction as capital A and A1 perpendicular to capital A. So acceleration of wedge along this line which I have drawn here. Which line? This line. Why that line? Because this is the contact surface and perpendicular to contact surface. I must take the components of acceleration. So wedge acceleration along this line is A sine beta. How A sine beta? It makes beta with blue line. So A cos beta is blue component. A sine beta will be the component along the line. So A sine beta. And what is A2's component along that line? That is A2 sine beta only. How? Because A2 is also in the same direction as A only. Okay. And A1's component will be A1 cos beta. If A2 has a component sine beta in this direction, okay, A1 will have component cos beta. In fact, this angle is beta. Angle between two lines is angle between their perpendiculars. Okay. So this is acceleration of wedge perpendicular to contact surface. This acceleration of both components of rod perpendicular to contact surface. That's my second constraint. So I have my first constraint. Okay. A1 cos alpha is A2 sin alpha. First constraint, that is with the with the right wedge, and I have the second constraint with the left wedge, and I have to solve these two for two variables. What are my two variables? A1 and A2. So let's solve them. So I'll take them to the next page. A sin beta, this equation A sin beta is A2 sin beta plus A1 cos beta. A2 sin beta plus A1 cos beta. That was my one equation, and the other one was A1 cos alpha is A2 sin alpha. A1 cos alpha is A2 sin. Okay, so I'll eliminate uh, maybe A2 from this. What is A2? A1 cos alpha by sin alpha into sin beta plus A1 cos beta, which I can write it as A1 into sin beta cos alpha plus cos beta sin alpha by sin alpha. So from here I can say A1 is A sin beta sin alpha by sin beta cos alpha plus cos beta sin alpha is sin beta plus alpha. I'll write it like that. Sin beta plus alpha. Okay. Okay. Now, what about A2? A2 should be A1 into cos alpha by sin alpha. A1 into cos alpha by sin alpha. Then sin alpha will get cancelled, right? So it will be A sin beta cos alpha by sin beta plus alpha. That will be A2. But I want the total acceleration of the rod. Total acceleration means resultant of A1 and A2. I have assumed two components. So it is root A1 square plus A2 square. So from here, acceleration of the rod is going to be root of A1 square plus A2 square. Is going to be this square plus this square under root. In that, this part is common in both the terms. Then you will be left with sine square. If you take that common, sine square plus cos square is 1. I hope you are understanding. When you square this, And when you square this and try to add, first this term is common in both, this square. Then you will be left with sine square here and cos square here, but sine square plus cos square is 1. So it will be a sine beta by sine beta plus alpha. That will be the acceleration of the rod. Is there a better way to do this? This has been a very long method. What is the better way to do this? There is a better way to do this. So I'll show you that. Let's take this diagram again. Okay. Instead of taking two components of acceleration, I can do a very clever technique. The clever technique is, you can assume the rod is going along this incline with small a. Why it should go along the incline? See, if I have a wedge and there is a wall, okay, if there is a block, it has to go along the incline. Nah? This is no different from a block. It has to be in contact with the wedge. It cannot go inside the wedge or outside. It has to go along the wedge, right? So I can say that this rod is going with an acceleration a. So I will draw its direction like this. It's going with an acceleration maybe a. And what is that angle with horizontal? It's alpha. So this angle is alpha. Okay. This acceleration, if you extrapolate it, it will make an angle alpha, right, with the horizontal. So I'm drawing it here. I'm drawing that acceleration here. Okay. And the perpendicular to this contact surface, I am drawing perpendicular to this contact surface. Okay. What is perpendicular to that contact surface? If I draw like this, that is, if I show it here, that is the perpendicular. The blue line is the perpendicular to that contact surface. Okay. Now, let's look at it very carefully. What will be this angle? This angle. See, the total angle is, this total angle is alpha plus beta. Can you see that? Let me show it with the marker. This is beta. This is alpha. So this total angle is alpha plus beta. Alpha plus beta. And from that you remove 90. So this is going to be alpha plus beta minus 90. This is going to be alpha plus beta minus 90 degrees. Okay. And this angle, I'm sorry, this angle, what will be that angle? This whole angle is 90. In that you remove beta. So this is 90 minus beta. This is 90 minus beta. Okay. My capital A is in which direction? My capital A is in the horizontal direction. Okay. My small a is in which direction? It's in this direction. What I have to do? I have to take components of this acceleration perpendicular to contact surface. Perpendicular to contact surface is this direction, that direction. Okay. So what is small a component along the blue line? A cos alpha plus beta minus 90. That should be equal to what is capital A component along blue line? A cos 90 minus beta. Okay. So you can write this as A. There is a rule, cos alpha is cos minus alpha also. For cos negative angle also, you can remove the minus sign and say it cos alpha. So if you multiply this angle with minus 1 and write it, it will be 90 minus alpha plus beta. Cos 90 minus alpha plus beta is sin alpha plus beta. And this will be a sin beta. So what is small a from here? From here, a sin beta by sin alpha plus beta. Can you see that? That's what we got previously. Where we got it in one of the methods. No? A sin beta by sin alpha plus beta. We got it in a very big way, but now I'm getting it in a much faster way. I got the same answer. I got the same answer in a much faster way. right? So this is how wedge constraints will work. Here I have only developed the constraint. I am not solving the complete system. If you want to solve the complete system, then you should give me the mass of the wedge, the mass of the rod, and then I can apply Newton's laws and solve it. No big deal. Okay. I can draw the free body diagram, apply Newton's laws and solve. Once I have the constraint with me, I can definitely solve it. No big deal. So this is the idea. So this is about wedge constraints, and we will use it in uh, many problems wherever we go. Sometimes, I will show you in the next class some very complex questions. Sometimes the constraint is already there. Without your knowledge, you have applied the constraint. See, for example, suppose I have a wedge which is fixed. Okay, it cannot move, and there is a block. And you say the block is sliding down, sir. I'll take acceleration this way. Means you already applied the constraint. How? Look, perpendicular to contact surface. This is the contact surface. In this direction. You are already saying wedge has no acceleration and block also has no acceleration. Why block has no acceleration? Because you already have taken it in this direction, right? So you, without thinking deeply, you already applied the constraint here. Okay, in that direction, sorry, in that direction, there is no acceleration for the block. You have not taken it, and wedge anyway is immovable, so it has zero acceleration. So sometimes the constraint is already applied. Okay, in such cases, again, you need not write it. So we will solve problem some 3-4 questions in the next class using wedge constraint, which are very complicated. I can have some 4-5 methods or 6 methods sometimes in some problems. We take different coordinate systems with pseudo force. I'll explain the concept of pseudo force also in next class. With pseudo force, without pseudo force, tilting the coordinate systems, assuming first the acceleration in the wedge frame, then writing it in ground frame, without assuming acceleration in wedge frame, directly writing it in ground frame. Different techniques are there. You must be thorough with all of them. Then only your clarity will be much better. So we'll do that in the next class. So any doubt still here? Is it okay? I went very slow. This is a very critical topic. I didn't do many slides, but I told you what is a wedge, and what is the wedge constraint and everything. So go through this lecture once again. Very important. All these lectures are very important. Many students feel Newton's laws are tough. Okay. It starts from Newton's laws and goes all the way up to rotational dynamics. They feel that these topics are going tough. So I want you to once again go through this lecture very thoroughly so that you'll be comfortable.